Yes, yesterday we stopped at the beginning of the instrumentation amplifier. But what did we say were the problems with the difference amplifier? Two main problems we discussed with the difference amplifier. Come on.
It could carry Visium.
Yes, it would amplify the common mode voltage, so we found the common mode gain. But we tried to solve that. How did we try to solve that? We added this potential divider at the input. But the problem with that is fine, and these resistors have to be very well matched, which is very tough. I mean, you cannot buy, nothing is identical to the other. It's a manufacturing process, there's always discrepancies, there's errors. So you can screen the resistors, and that's what happens when you buy more expensive resistors. It means that they're screened for their values, right? So instead of the manufacturer telling you, okay, these are 10 kilo ohm resistors, plus minus 20%. These you'll get them for cheap. If you want 10 kilo ohm resistors, plus minus 5%. They're the same resistors. He's not telling you something different. They are not. But what they're doing is they're passing them through tests. So these tests cost money, so you pay more. So you want 1% error, you pay more. 0.5% error, you pay more. But it's the same resistor. Right? And then the resistance values change with temperature, right? So it's a messy process here. So there is gain to common mode unless these resistors are perfectly matched, which is a problem. The other thing we said was, anytime you see that there's a resistor at the input, right, and a path for current to flow, there's an easy path for current to flow like what we have here, then we said that our input would be low. Because our input will be 2R1, and the gain of this circuit was R2 over R1. So we wanted the gain R1 to be small, which means that our input of the amplifier will be small. So you cannot really have a large gain for the amplifier unless you compromise your input impedance, right? So that was the problem. So we went away and said, okay, fine. This is a nice circuit. It does some nice stuff for us, right? It affects the difference of the input. It allows us to look at the differential signal, not a single-ended signal, right? So it's a nice signal. It's a nice system from that perspective, and it has a way to deal with the common mode voltage somehow, right? But it has these limitations. So the alternative is something called the instrumentation amplifier, and this is really the workhorse of the measurement industry. So what we did here, you can buy this as one package. Not you don't need to build it separately. You can build it discrete, or you can buy a box of an amplifier, just a separate box. Yeah. So you can both ways are possible. Yeah. So what's happening here? So here I have the input is going to my non-inverting input. My input signal is going to my non-inverting input, my plus. The other input signal is going to my non-inverting input, and this looks exactly like my non-inverting amplifier. Exactly same non-inverting amplifier. So this is a non-inverting amplifier. This is another non-inverting amplifier that we have here. The gain of the non-inverting amplifier is 1 plus R2 over R1 multiplied by the input. Right? This is the gain for the non-inverting amplifier that we talked about before. So here at this node, at this node I will have this voltage, and here at this node I will have this voltage. What if I have a common mode voltage on VI1? Go back to your non-inverting amplifier. What's going to happen? It will pass through, and it will be amplified by the same gain. Right? It will be amplified by the same gain. Right? So, which was the main drawback for utilizing the inverting input with signals that have common mode. You cannot deal with it. The common mode will pass through and it will be amplified. Right? So that was a problem there, and it's still a problem here. But the nice thing, what we did here is we put a difference amplifier after it. What does the difference amplifier do? A difference amplifier, if I properly tune the resistors, I can get rid of the common mode voltage. The other problem it had was the input impedance was low if I wanted a high gain. So how did we solve this? So the common mode voltage will pass through. This circuit will still see the common mode voltage passing through with the gain, because I still have my non-inverting, right? But if I properly choose the resistors, then I can sort of eliminate it, right? But that was still the same as my previous circuit. What did I buy myself? So what I bought myself here is, in the difference amplifier, for me to have a large gain, I had to compromise input impedance, right? So I want something that buys me some advantage over the previous circuit. The advantage over the previous circuit versus this circuit is now I can have my gain stage here in the non-inverting amplifier section, the front end, right? And then I make this low gain but high input impedance, right?
Without actually paying too much.
I don't pay on I don't lose on my R input,
Yeah.
right? So my problem with this previous circuit was two problems. And one of them still persists here, okay? One of them still persists in this configuration. And I will solve it in the next configuration, right? People, we keep solving problems here. So with this configuration, and with the previous configuration, I had the problem of, for me to eliminate common mode, I had to have perfect matching, which is very tough. But this problem still persists here. With the previous configuration, I had low input impedance if I wanted high gain for the difference amplifier. Right? I only had the difference amplifier, and the difference amplifier had a gain of R2 over R1. And my R input for the difference amplifier was 2R1, two of these. Right? So, and the gain was R2 over R1 for the difference amplifier. So, in this case, it's going to be R4 over R3. Right? So the R2 in the previous case, so let me write R4 over R3 better. So the gain for the difference amplifier is R4 over R3, and the input impedance is 2R3. Right? R4 over R3, right? For me to have large gain, I need large R4, small R3, right? Small R3 means small R input. Small R input, right? I'm not going to go with a large gain on this stage. I will go with a small gain. So if I have a small gain, let's say unity gain, I can have R4 over R3 equal to each other, for example. They can be large, 1 mega ohm, 2 mega ohms. I can make them large. Because the gain, I don't care. I'm not adding gain to this stage. I'm utilizing the front end to create the gains. Right?
But
So
isn't the game, doesn't it have also VCM?
exactly, which is not a good thing about this circuit, and we will solve it with the next circuit. So this is a problem, and it means that what? It means that I'm also going to be limiting my following stage and my output stage of these amplifiers if I have a common mode signal, because the common mode signal will, again, remember the amplifier output cannot exceed the supply voltage, cannot exceed. So if I have a signal that has my measurement as well as common mode voltage, and I amplify my common mode voltage, what is that doing to my output? It's eating from my ability to send the signal through without clipping it or changing its frequency content, right? So it's still a bad thing. So this common mode problem is still an issue that we need to deal with. So we dealt with the input impedance, and we dealt with the common mode in two funky ways, right? Nice, bad, it's okay, but not great way. So does everybody see the limitation of this circuit? So we went away from this circuit and we introduced a small change. All we did now was remove this ground and make these two resistors one resistor. Let's see what that buys us. Okay. What does this buy us? So I removed the ground. Right? All I did was remove the ground. And I just put, fine, a resistor 2R1, whatever value of resistor you want. So now I have an op-amp with negative feedback, right? From the output to the inverting terminal, from the output to the inverting terminal, right? What does negative feedback buy us? Negative feedback buys us that the difference between these nodes is pretty much zero, so it's like the same potential, which means that if I have VI here, I also have VI. If I have VI2 here, I also have VI2 here, right? And here, this is the output due to this input, whatever it is. We'll see what it is now. And then this is the output due to this input, right? And I also have VI1 here because of the negative feedback that I've placed. Now, what is passing through to your difference amplifier? That's what we want to see, okay? Because we want to see what we did to the limitation of the previous circuit was we were amplifying the common mode signal as well. So now let's see what's happening to the common mode signal. So because VI2 is here and VI1 is here, the current flowing in this branch is due to VI2 minus VI1. Right? I have VI2 here, I have VI1 here, so the current flowing here is the current due to it's the current due to the difference of the voltage divided by 2R1. So it's VID over 2R1. That's the current flowing in this branch. What does that mean what does that mean for the common mode signal? Common mode signal is a voltage that is the same on this input and this input. If I now subtract both inputs from each other, what does that mean for the common mode signal? 0. Right? I have V2 plus VC here, VCM here, V1 plus VCM here. Right? I subtract them from each other. I have V2 minus V1, VCM minus VCM. They're gone.
Why would you subtract
No, because the voltage difference across this resistor is this voltage minus this voltage. If you want to calculate the current, it's this voltage minus this voltage. So now across this resistor, I have my signal V2 minus V1, my differential signal, right? And I lost all the common mode signal across this resistor, right? I want to see if I'm able to transfer this nice clean signal without this common mode signal to my amplifier without amplifying the common mode signal. Common mode signal, it's present. I mean, it's here. It's coming in. But if I'm able to find a tricky way to make them cancel each other before applying a gain to it, then that's great. So now let's look at what voltage I have between these terminals. Because this is the voltage that's going to be applied to the difference amplifier. The difference amplifier gain is what? R4 over R3. That's the difference amplifier gain. So obviously I'm going to take this gain and multiply it by the gain that I'm getting from this previous circuit, and that's what we'll plug in here. Okay, so how do I do that? So one easy way to do that, for example, is to apply Kirchhoff voltage law around this loop. I have a loop here, right? This is a nice loop here, right? So this current is flowing here, this current is flowing here, this current is flowing here. I know the values of all these currents, right? If I know the value, since this is VID over R1, right? This current here is VID over R1. The current here is 0, which means that all this current is flowing also in this resistor. And also here, the current is 0. That means all this current, VID over R1, is also flowing through here. So now, this is current flowing through here, there's a voltage drop. This is current flowing through here, there's a corresponding voltage drop. This is current flowing through here, there's a corresponding voltage drop. This voltage drop is equal to VID 2R1 times R2. This is VID divided by 2R1 times R2. And the voltage drop across this resistor is VID 2R1 times 2R1. I times R. No, so the R1s will cancel. So the R1s will cancel, right? So it's the voltage drop here is 2R1 times VID over 2R1. So the 2R1s cancel. So I'm only left with VID. Okay? So now let's apply that. So this is going to be the voltage that I have here. Right? So let's see what
And that voltage is equal to each other. It's equal to each other. Those two voltages. See, there's two nodes, right?
Yeah.
And that
I want the voltage. I want this voltage.
Across the.
I want the voltage across that. I want the voltage that's going to my difference amplifier. Because now the difference amplifier, I made it high input impedance, right? So no current will flow. Right? That's the trick here. Okay. So you made the gain here. We want to make sure we make the gain at the front end, so that I keep a difference amplifier with high input impedance, so I don't no current's going to flow inside here, right? So then I go back to my nice ideal equations for the difference amplifier, and I can just use its gain R4 over R3, right? So the voltage here is equal to what? It's equal to this voltage. So I have this voltage plus this voltage plus this voltage is equal to this voltage here. So VID over 2 R1 multiplied by R2 plus VID is the voltage here across this plus another one of these, VID over 2R1 times R2. So this goes away, the 2's goes away, right? So I'm left with VID R2 over R1 plus 1, right? That's what I have here. Find the 2's here. Right, so VID 1 plus R2 over R1 is what's going through here. It's like I've created a non-inverting amplifier with, like that eliminates common mode from the input. Right, and that's what I have here. So it fixes the first problem as well. So we had fixed the second problem, which is the low input impedance, by making this a low gain amplifier, right? So I make this low gain but high input impedance, and now I can control the gain of the front end, because at the end I want, so now I would put this here, 1 plus R2 over R1, so this is V output over VID, right? So V output, VID is the difference between them, between VI1 and VI2. So the gain from input to output is R4 over R3, 1 plus R2 over R1. I'm able to control the gain of the front end using R2 and over R1, and they will not affect my common mode rejection capability. I'm able to control the gain of the second stage to make it low, so that I do not lose my input impedance for the second stage of the amplifier.
I don't get how you fix this. The first
Which one? The first
yeah,
problem?
the second.
Our input impedance? Well, we said that the difference amplifier has a problem of low input impedance, right? That was the problem from the previous circuit here. So this low input, that was the problem with the single difference amplifier by itself when we want to make it high gain, because again, the gain of the difference amplifier is R4 over R3, and the input impedance of the difference amplifier was 2R3. This was the input impedance, this was the gain. If I want to make the difference amplifier have high gain, I need R4 to be big and R3 to be small. If R3 is small, the input impedance of the difference amplifier is low, so I would be loading my sensor. So we didn't like that circuit, so we went to the instrumentation amplifier. The instrumentation amplifier in the previous case, with the ground connection, already solved this. This one solved the second problem. So the previous one with the ground connected here already solved this input impedance issue, because we took the gain, we did the gain here. We controlled the gain of the signal at the front end using the non-inverting amplifiers. And then we made the difference amplifier low gain. If I make it low gain, meaning R4 can be low and R3 can be high, which means the input impedance will be high. So I can have a high input impedance for my difference amplifier. That's nice. How about the input impedance for the non-inverting amplifier? What's the input impedance? Sheikh. What's the input impedance for my full instrumentation amplifier now? Fine. The input impedance for this stage, we made it high, because we don't want to load the previous stage of the amplifiers. That's fine. So we know we did that. How about the input impedance of my full instrumentation amplifier? How am I affecting my sensor? What's the input impedance? Infinity, exactly. So now I have an infinite input impedance, and I have zero output impedance because this is an op-amp that has no output impedance. So I have a very nice circuit now, right? I have infinite input impedance, zero output impedance. I'm rejecting common mode, and yeah, so I'm rejecting common mode, and I'm applying a gain that is not and I'm not dependent on the common mode rejection on tuning these resistors. Remember that tuning these resistors was a problem with the common mode signal passing through, right? So this difference amplifier had two problems: the common mode and R input. The previous circuit and this circuit solved R input easily, and this configuration, after we removed the connection, solved the common mode signal issue, which gave us relaxation on the choice of on the use of R3 and R4 that are not so well trimmed and tuned to each other. Solves all the problems. This is a nice. I don't have another problem. There's no problem here, so there's no new circuit to solve. Okay, so we solved all the problems that are available in this without considering some more non-ideal, of course. We just consider the common mode and input impedance issues. Right? Of course, there are other problems that will come up here. Also, I don't have to, since I already also got rid of, so here we said that R4, R3, making them so equal to each other and precise resistances is no longer very, very important anymore because I got rid of the common mode signal here, right? Also, what else is interesting here? The gain of this stage was 1 plus R2 over R1. R1 is common between both amplifiers. But what if R2s are not, here I relax the precision of these resistors. How about if I relax the precision on these resistors as well? Right? When I relax the precision on these resistors, made it easy to design, right? And if temperature changes and blah, 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 it's okay. I'm still happy. I'm still performing my function. But what if I also relax the conditions on these resistors? So what's going to happen to the voltage here? This was the voltage, right? It was VID. It was VID plus the voltage drop here plus the voltage drop here, right? Let me write it again, but now with different values for R2, okay? Because when we made it same values for R2, we make this 2 and we cancel with each other, right? Huh? Yeah, it won't cancel. So, but if it won't cancel, is that going to hurt us? Let's see. I will erase, okay? Because, too much. So the voltage here is this drop plus this drop plus this drop. We know this is VID, right? Plus VID over 2R1, which is shared, multiplied by R2, plus VID over 2R1, which is shared, times R2 prime. Right? So I can write this as VID outside, right? And then R2, 1 plus, okay. 1 plus, R1 is the, 2R1 is a common denominator, right? And I can write this R2 plus R2 prime, right? And then this is what I see here. This is going to then be amplified by what? By the difference amplifier gain, which is R4 over R3. So let me erase this. Multiplied by the difference amplifier gain, which is R4 over R3. Did this bother me? It just gave me a gain that is a little higher or a little lower. But it still did not pass the common mode signal through. Right? That's the beauty of this circuit. So now I don't have to have very precise matching between the R2s, and I don't have to have very precise matching between the R3s and R4s, and I get everything I want. I have this amplifier not loading the previous stage. Yeah, yeah. I mean, this is V output over VID equals blah blah blah. This is the gain. I'm only writing the gain. Okay. So this is the beauty of this circuit, right? It buys me everything I want from an instrumentation perspective. Okay. Okay. Yeah. So that covers the. This is the gain with the resistors equal to each other, and then these are the three problems. The common mode signals, and then perfect matching between the resistors issue in the front stage, and then the perfect matching between the resistors in the second stage. So these are the three problems we discussed, and they talk about them, and they derive the equation that we derived, and then they derive the equations with the R2s not equal to each other, and then yeah, and they just discuss this a little bit more.
We can always use the one who solved the two problems. The circuit
Yeah, this instrumentation, this last instrumentation amplifier.
is the one we will use.
Yeah, I mean, I would use this one. It doesn't. I mean, you don't lose anything, right? You just remove the a reference point, right? That's why selection of grounds is not haphazard, right? People, think of how current is flowing and stuff like that before they just connect everything to ground. So yeah, so this is the workhorse, I would say, of the industry. But again, remember here we still didn't consider more non-ideal effects like internal offset voltages and bias currents here flowing. So there's still more problems to solve. But basically, this is what this instrumentation amplifier section talks about. They just apply the equations and they ask you to calculate some gains. I'm not going to. It's a very basic exercise. Okay, now more applications. So we looked at applications for amplifying the signal, inverting it, and non-inverting it, and we looked at applications of effect of common mode, etc., etc. We looked at adding and subtracting input voltages. Now we will look at and everything we did not have any capacitors in there, right? There were no elements. There were all resistors around the amplifier op-amp. So now we will introduce some circuits with capacitors in different places that will help us do time-dependent things. So like integration and differentiation, right? So and filtering, of course. So in general, this looks like what configuration? The inverting configuration, and inverting configuration has the gain of R2 over R1. Here I generalized, it's Z2 over Z1. It's the same, the derivation is the same if you just use your circuits analysis. Yeah. So that's the main difference. So let's look at a general Z2, for example, where that has some capacitor in there, right? So just as general introduction.
Okay, quick question.
Yes.
I guess it's outside the topic, but what exactly does a capacitor do, like in a circuit, AC circuit? I know what a capacitor does, it's a component, but what does it do? What characteristic does it do in a circuit?
Again, we will see here that again the basic relationship between current and voltage across a capacitor is going to help us understand how the circuit here will behave as an integrator or a differentiator. So what the circuit does is basically accumulate the current, the charge on its value, and correspondingly creates a voltage, right? So IC equals C dVc by dt, or Vc of t is equal to 1 over C integral of IC dt. So if you are gonna place dt, if you're gonna have current flow through a capacitor, like what are we gonna do here? This is remember, this is an op-amp circuit with negative feedback, right? I have negative feedback. Since I have negative feedback, these two voltages are ideally the same, which means the voltage here is 0. So which means that I can calculate the input current as VI over R1, right? Where is this current going to flow? Op-amp is ideal, does not flow inside. So the current's going to flow here. Now this is 214. You have I here that is constant. Let's say assume this is a DC input, so this is a constant current. Let's say 0.1 milliamp, for example. That's going to flow into an RC circuit. what's going to happen to the voltage, because the voltage across the RC circuit is going to be the negative of the output voltage, because this, again, the output voltage plus this drop, right? Since current is flowing here and here, there's a voltage drop across this parallel combination, and then this voltage is 0. So the output voltage is equal to negative of this drop, right? So now my problem is, how do I calculate VC? Multiply by what? The current? Yeah, but what is the current? Remember, this is the 214, the transient analysis stuff. How capacitor is charged initially or not charged. So what's going to happen to the... Yeah. And then what happens at infinity? What happens what happens if you keep pumping input DC current into a circuit like this? Capacitor becomes what?
Open circuit.
Open circuit. If a capacitor becomes open circuit, then I just have this resistor. So at infinity, if I keep pumping, keep this DC source there, what is this going to look like?
An inverting amplifier. Just a normal.
Inverting amplifier at infinity. If I keep this DC signal in there forever. If I put a DC signal in there, okay, if I place a DC signal in there, after a while, this capacitor becomes an open circuit. Sure, I agree. Sure, yeah. How about if I remove this capacitor? That's the next step I wanted to do. How about if I remove this resistor? Sorry,
Okay.
if I remove the resistor. Yeah, the gain of the circuit. Okay, at infinity, the gain of the circuit becomes R2 over R1. Negative R2 over R1, because this is like the inverting amplifier. If I keep R2 in there, how about if I make R2 infinite?
R2 infinite?
Yes, and I keep a DC.
Gain is infinite.
Huh?
Gain is infinite.
The gain is infinite for DC inputs, right? So if I draw my magnitude versus frequency, I get something like this. You agree? At DC, at low frequencies, the gain is infinite. Actually, infinite. I don't know. Infinite, whatever. It's infinite at DC, and it will be decreasing beyond. When I put some AC signals, because the capacitor will come into the circuit again, and I will have some impedance playing its effect, and the gain. So here I put R2 is infinity. If I place R2 back, what happens?
Go back.
Hmm?
Go to, so it's going to
So if I remove R2, the gain over the gain versus frequency curve is like this. Do we agree?
Yeah.
Because the gain is this is infinite. So the effect of the resistance is adding infinite gain, and the fact that I have if I make R2 infinite makes the gain infinite. And the fact that the capacitor is open circuit at DC means that, fine, it has no effect on what's happening at DC if I remove this resistor. Right? What does this look like? This is magnitude over versus frequency. This is the magnitude of the transfer function T of S versus frequency. It looks like what? Yeah, body plot. What does the function look like? 1 over S. 1 over S, right? 1 over S looks like this. Or 1 over X. When you plot...
You mean 1 over j omega?
1 over j omega or 1 over S. How do you plot that? You plot the this is your transfer function. If your transfer function is 1 over S, what is its magnitude? Its magnitude is 1. And at DC. Sorry, so its magnitude is 1 at where? At S equals 1.
So I don't understand why the 1 over S looks like this. Like this.
X of t, okay. Plot x of t equals 1 over x. Sorry.
No, 1 over X doesn't look like it.
X of t is equal to 1 over t. Sorry. X of t is equal to 1 over t.
So it looks like this.
Looks like what? 1 over t.
Yeah, it doesn't
It
cross.
has a vertical asymptote at X equals 0.
It doesn't cross the
Doesn't cross
I think
the...
x-axis.
It goes to infinity like this. And then on the other side, it was like
Never
this.
reached zero.
No, at t equals 0, what is the value?
Yeah, positive infinity.
Infinite. And at t is very large.
Infinite.
At t is very large.
Zero.
It's
Opposed
zero.
to zero.
T is very large. It's 0. Some t is infinity. It's 0. Right?
Yeah, but that
So
was
this is on a
line.
linear scale. Sure. This is a linear scale. Remember, we plot it in dB. In dB, what we do is we actually shrink this axis. So this here is going to look like a straight line when you plot in dB.
So this plot was big.
Yeah, the plot is in dB. Sorry.
And
So
it will cross the x-axis.
it will cross the x-axis at when? At where?
10.
Where will it cross the x-axis? Remember, 20 log the magnitude of the function at t equals 1. The gain is 1. 20 log 1 is 0 dB.
Okay.
0 dB.
At unity.
And for this, yeah, for s is equal to 1, for example, in this case, right? In other circuits, we will come up with, at s, at omega is equal to omega naught, right? Remember the omega equal to omega naught? What?
This is the first time we ever graph using log. I think in any course ever. So I think you should take it slow with this.
Sure, but go practice. I have no problem with that. I'm happy to work with you on that, man. But again, a linear scale is different than the log scale, right? So
Of course.
we in the linear scale, what will look like something in the linear scale will look different than the log scale, and that's why we actually plotted log scale. Right? It gives us some better intuition about what's happening versus frequency. Here, this is what's happening versus time. Right? This is what's happening versus time. Yeah. Right? So anyway, that being said, let's go back to the way the text is going about this. Okay. That being said, let's go back to the way we are deriving the gain for the inverting amplifier. Again, what's the inverting amplifier gain? In general, V output of S over V input of S is equal to Z2 of S over Z1 of S. Right? That's the negative Z2 of S over Z1 of S. Right? That's the general value. So Z2 is this, and Z1 is this. So this is R1, and then Z2 is this parallel combination. Right? So I can write it in terms of impedance, or sometimes, since it's 1 over R plus 1 over SC, I can also write them in terms of admittance and write it R plus SC. Right? It just makes it easier for me. So that's what they did here. So V output of V input is equal to 1 over Z1 multiplied by Y2. Right? Instead of Z2 over Z with a negative sign. Instead of Z2 over Z1, they brought the Z to the denominator and wrote it in terms of Y, admittance. Right? So what is the admittance of this? It's R2 plus SC2. 1 over R2, sorry, plus SC2. Right? So it's 1 over this impedance plus 1 over this impedance. This impedance was 1 over SC, so it goes to the numerator. So it's minus 1 over R1 over R2 plus SC2R. So they just made some manipulation of the denominator. So the Y2 was originally 1 over R2 plus SC2. So they put that here, multiplied by Z1, which is R, and then they divided by R2, or they multiplied by R2, or divided by R2. They multiplied by R. They divided by R2, I guess. Yeah, they divided by R2. No, they multiplied by R1 here, right? So they have 1 over. Let me write it down. Equals minus 1 over Z1 is R1, and Y2 is 1 over R2 plus SC2, and then they just simplified that. So R1 over R2 plus SC2 times R1. Yeah. Why is this interesting? Right? Why is this interesting? Because it starts to look like if I make this 1, it becomes like the single time constant circuit form that we had in the table. It was what? It was a DC gain over 1 plus S divided, multiplied, whatever by something. Right? So it's going to start looking something like that. So I can divide by R1 over R2, top and bottom. So it becomes R2 over R1 in the numerator, and then 1 plus SC2 times R2 in the denominator. So this looks exactly like my low pass single time constant circuit transfer function with a DC gain of what? What's the DC gain here? DC gain minus R2 over R1, right? So if the DC gain is of this circuit is minus R2 over R1, if R2 goes to infinity, what happens? If R2 goes to infinity, I have infinity over 1 plus SC2 infinity, right? So,
Oh, I'm sorry.
at these, yeah, this is what happens. Yes, they would go away at AC, right? And I would be left with what? You know, at DC, sorry, at AC for AC frequency for high frequencies. This is what? This is even larger because I'm multiplying something large by something large. So at high frequencies, if S goes to infinity and R2 goes to infinity, then infinity over much larger than that is 0, right? So this will go to 0 at some point, right? And then how about at DC? R2 is still infinity, but S is 0. Then this goes away, and the gain is infinite. Right? So it becomes, if R2, this is what we were talking about, if R2 becomes open circuit, if I remove R2 from this circuit, I'm creating a 1 over S type transfer function that is going to be applied to the input. What is 1 over S in Laplace? Remember 1 over SC is the integration of S. 1 over S is like an integrator.
Yeah, so it's like 1 over C times S squared, something S squared.
Remember, IC equals C dVc by dt. And VC is equal to 1 over C integral IC dt. So IC is equal to SC. And VC is equal to what? 1 over SC. Remember your Laplace? You were going around the loop. If you wanted to find the voltage across the capacitor, you were calling that, you were saying the voltage drop across this capacitor is 1 over SC.
Yeah.
The current is SC. Where is this coming from? It's coming from these relationships. Remember? No?
We didn't take the last transfer in the same
214 you did not take?
No,
I think you multiplied this for, and we even took it like,
but we didn't take
badly.
it like in circuits or anything, so we can't see the connection.
I think it was another course, like,
No.
or you're mixing 215.
No, I'm not teaching 215. I don't teach this in 215 actually. I'm very surprised. Anyway, regardless, let's go by step. If you did not take this Laplace, you did not apply Laplace on circuits.
I was thinking in Laplace in normal terms, and that was wrong.
Okay. You will have to do that in 420 anyway. So in 420, Dr. Hazem, I'm sure, spends a lot of time on that. Yeah. So in the future, you will do that. So for now, let's just follow our gain calculations that we've been doing. So Z2 over Z1, we simplified. We put it in the format that is like the low-pass single-time constant network that we've studied before, which means it has some DC gain, and it has some corner frequency. The corner frequency is what? Is the frequency at which the gain becomes 0. Minus 3 dB, right? So this is my single-time constant circuit. I will have my corner frequency here at omega is equal to omega naught. This is omega over omega naught, right? Omega equals to omega naught. This is 1 here, and this is minus 3 dB. What is my minus 3 dB frequency, or my corner frequency, or my break frequency?
It's C2, 1 over C2.
Exactly. So it's 1 over C2 R2, which is also the time constant of the circuit, right? So So that's this transfer function. If I make, this is not, okay, now it will make sense, hopefully, okay? If I make, what does this mean for the signal that's coming in? This is my gain versus frequency, right? If I have a low frequency signal coming in, it will be amplified by, or it will be multiplied by the DC gain, right? And it will come out. If I have a high frequency signal, it will be attenuated by this value of my gain at this point, right? And then it will come out of my amplifier. That's fine. What if I keep making R2 larger? What's going to happen to omega naught? Yes, exactly. So what's going to happen to this point? Move to the left, move to the left, right? So if I move this to the left, then we go back to my straight line. Is this okay? What does that mean now? What does that mean? It means that the gain at DC, if I put a DC into this system, right, it's going to be amplified with a gain of infinity. Very large gain. Very large gain at DC, right? So think of applying now a DC to, if you integrate. This is a better way to explain. So if you apply this signal through here, what do you get at the output? Integrate 5. You get a ramp, right? This ramp, does it stop? Your input does not stop. Is the ramp going to stop?
No.
Does not stop. Which means that the gain for the DC signal, when you pass it through an integrator, is infinity. To go to infinity, to keep going to infinity. Well, fine, op-amp will saturate, that's fine. But this is what this means. This is a better way to explain, right? Not Laplace. It's a better way to explain. So hopefully this is clear now.
So that's why we have bonds. And
That's why?
we don't use DC. That's why we use AC.
That's why integrators are not good with DC circuits.
We use AC.
Developing an integrator for a DC input is a problem, because the gain for any DC input will be infinity, right?
And that will saturate.
So-
Plus or minus.
Exactly. At infinity, it will saturate to something after some point in
If it's
time.
in a non-inverting, it will saturate to the positive value. If it's an inverting, it will saturate
Exactly.
to the negative.
But what if I don't? What if I keep now R2 to be large, but some value? This omega naught will not go to 0, right? And the gain will not be infinite, right? Gain became infinite, and omega naught went to 0 when I made this R2. When I made R2 very large, omega naught went to 0, and my k went to infinity, right? This is my k went to infinity, and my omega naught went to 0. If I keep R2, and we said this causes a problem, so we will see that if I remove R2, I have an integrator, ideal integrator, very nice, but it does not work at DC. If the signal has any DC component, it will not work. And we will see that, fine, if the common mode signal passes through, what is it? Common mode signal is maybe a DC value. If I have it offset, it's a DC value. So which means that anytime you build any circuit, there will definitely be some DC value in the signal coming through. So an ideal integrator would not work. So practically, when we build an integrator, we have to put an R2. And this R2, what will it do? It will move this omega naught from 0, move it a little bit to the right. So I still have something like an integrator right after my DC signal. So for my DC, I know the integrator will make something like a ramp and will, large gain. Fine, I made it with a large gain, but not infinite, right? Not infinite. And I did that by keeping R2 to a fixed value, which moved the corner frequency a little bit away from the DC so that I don't have infinite gain at DC. Okay? So, we're fine. That's why we started with the general circuit. And then we will, okay, since this is a transfer function of the general circuit, we know the DC gain, we know the input, we know the output. We've studied this before, I'm not going to go and calculate this. And then we went to the integrator right away. How does the integrator work? The integrator has a current coming through. due to this voltage. Again, I have feedback. This is the ideal integrator. Remember, I removed R. Right? There's no R here. Since there's no R, then we will have this problem with the infinite gain at DC. This current coming through here is due to what? VI over R. Since I have feedback and these two are the same voltage. So this current comes through here. It will go through the capacitor. Current in a capacitor is equal to IC equals
CV by
sorry, current through the resistor is what? VI over R. And this is the same as the current through the capacitor. So it's a DC current, it's a fixed current that I'm putting through this capacitor. So I'm putting a fixed current through a capacitor. What is the corresponding voltage? VC is equal to 1 over C integral of IC dt. And V output is equal to minus VC. Right? This is V output, this is VC. V output is equal to minus VC since this is 0. So V output is equal to minus the voltage across the capacitor. The voltage across the capacitor is equal to the integration of the current through the capacitor, which happens to be VI over R. VI is something that can change, right? So I keep that inside the integration. And then outside the integration, I put 1 over
CR.
RC or CR. And then, V output is the negative of that. So it's negative of 1 over RC integration of the voltage across the capacitor. Fine, if the capacitor somehow has initial voltage across it, you would need to subtract that from there or add it. All the problems, I think, in the homework, they assume 0 initial conditions, yeah. But the capacitor can have some initial voltage, right? It can have some initial voltage across it, yeah.
where did the negative sign come?
The negative because it's an inverting amplifier.
No, I mean in V naught.
Because V output plus VC is equal to 0. So V output is equal to minus VC. V output is equal to minus VC. Okay? Yes?
I don't see.
Right. So here, this voltage plus this voltage, and this is 0, is equal to 0. So this voltage plus this voltage is equal to 0. So this voltage is equal to negative of this voltage. Okay? So there's a loop here. This loop, Kirchhoff voltage law around this loop. There's no voltages here, and this plus this are equal to 0. Right? So they're equal to the opposite, negative of each other. Okay? So that's why the output is equal to minus 1 over RC integral of the voltage across the capacitor, minus some initial condition. The gain of the circuit, in that case, is, as we said, if we derive from the previous derivation, we just made R2 infinite, and we made, we just made R2 infinite in the previous derivation, and we were left with minus 1 over SCR. If you go back here, I think they derived it here as well. V output over V input. So V output, they derived it by V output over V input. So V output is the voltage across this capacitor. Voltage across the capacitor is 1 over SC. Or V input is what? V input is V input. So, or, Z2 over Z1. I think if you do Z2 over Z1, what is Z2? That's the easiest way to do it, probably. What's Z2? Remember the gain of the circuit, the gain of the inverting amplifier, V output over V input of S in the general case is equal to Z2 of S over Z1 of S. Z2 is 1 over SC, negative, sorry, 1 over SC, and Z1 is R, right? So you just bring minus 1 over SRC. Okay, so that's the gain of the circuit in the frequency domain. If you plot that, just plot it for different values of frequency and different values of R's and C's, and take 20 times log, you will end up with a straight line. This straight line has a slope of minus 6 dB per octave, which is equal to minus 20 dB per decade. So if the frequency is multiplied by 2, you drop 6 dB. If the frequency is multiplied by 10, you're going to drop 20 dB. Okay? That's what this means. What else? And then, of course, when does this magnitude, when 20 times log 1 is 0, so when will this become 1? At S equals, when does this become 1? The gain, when does the gain become 1? S no, when does the gain become 1? When does the gain have a magnitude of 1? When S is equal to 1 over CR. Exactly. So at 1 over CR, 20 times log of the magnitude is 1, which is 0 dB. Right? So it will cross 0 dB at the 1 over S at this frequency S equals 1 over CR. And it will have a slope of 6 dB per octave. Okay? This is known as an integrator, inverting integrator, because it multiplies things by a sign, or a Miller integrator because of the guy that worked on this initially. They go through that. And again, it has a magnitude of 1 over SC without the negative sign. And if you look at the phase, what is the phase of this? What phase is the output signal going to look like versus the input? What? The phase. The phase of, again, look at the phase. Phase of the top. This is, okay, so the phase, so I have a negative, okay? The negative causes a 180 phase shift, right? So this is causing the 180 phase shift. And then I have the phase of the top is 0. Phase of the bottom is? No, it's 90. No, so you bring it to the top if you want. Negative 90. So it's 180 minus 90.
270.
180.
Minus 90, 90.
So it's so the minus sign is causing 180, right? The minus sign is causing a 180, and then this 90, I can bring it to the top as a minus another 90, so I can make it minus 270. So either minus 270 or
No, actually it's plus 270 or minus 90.
plus 270 and minus 90. No, I think the way we. So maybe I did the 180 wrong, right? So 180.
180, I think it's
180 is this way,
this way, yeah.
right? And then,
It's positive, it's positive.
right? So 180. Let's assume this is positive and this is negative. So this will be my positive rotation, and this will be my negative rotation. So this caused the minus 180 phase shift, and then the 90 in the bottom went to the top
Minus.
with another 90. So it's either minus 270 or 90 degrees. Right? So the output will be phase shifted by 90 degrees with respect to the input. Okay?
So the 180 degrees is a negative. So it doesn't add 180, it subtracts 180.
It's phase shifts by 180.
Yeah,
Phase shifts by 180.
Where?
I mean, it flips it by 180. Huh? I mean, it doesn't matter if you have it, because we're talking about sinusoidals anyway, right?
Okay.
So 180 means it's just the opposite, looks the opposite. Yeah.
Yeah.
Right, I mean, sorry, I didn't draw the opposite
Basically, just
properly. But 180 will delay by 180 degrees.
Yeah.
So you delayed it by 180 degrees.
The peaks will like flip.
The peaks will flip, and then you've delayed it by another 90 degrees.
That's delayed by 270.
So it's delayed by 270, or you advance it by 90 degrees, right? So that's what this thing did. Yeah. But that's why frequency domain plots are nice, because then you will plot, now you plotted magnitude and phase. You plot magnitude, and the phase is constant. Phase with frequency is going to be constant, just plus 90 degrees. Time is up? Okay. So anyway, and then we talked about, so the time constant of this is 1 over CR. Here they talk about, here they talk about what we talked about before, okay, with the capacitor only, like we said, the gain at DC is infinite, right? 1 over SCR. If 1 over SCR, S is 0, then the gain is infinite, right? 1 over SCR, 1 over 0 is infinite. So the solution is, with integrators, practically you have to add this resistor, which we just derived before. And we talked about how it shifts the corner break frequency, right? So for a practical integrator, you will add this parallel resistor. For an ideal fictitious integrator, the circuit is what we talked about here. only a resistor, only a capacitor. Right? So we will stop here. So this is again, this is I will do this example. I think it's a nice example. I will do this example next time on the integrator, and then we'll move on to the differentiator. I think Sunday, I will